Hello, Matthews Gatos here. Welcome to our first Chapter 5 video. In Chapter 5, we're going to be covering trigonomic functions and their graphs. And in 5.1, we're going to look at the sine and cosine graph. So let's look at the the unit circle that we did in the previous chapter. So here's the unit circle all the way around in degrees. So what I want to do is, I know that the x-coordinate is cosine and the y-coordinate is sine. For example, 120 degrees, cosine of 120 would be -1/2, and sine of 120 would be √3/2. So I'm going to use all of these points because I want to look at what the cosine graph looks like and then what the sine graph looks like. So I'm going to create a table of values where in yellow here I'm going to use all of the degrees. That's going to be my x-coordinate. And then the y-coordinate that goes with it is going to be my cosine value. So for example, I'm going to graph the point 0 and 1, 30 and √3/2, 45 and √2/2. And then by connecting those dots, I can see what the cosine graph is going to look like. So again, x will be degrees, y will be the cosine of that degree. So I put those into a table of values. There's all my degrees, there's all my cosines, okay? So just so you can recognize some of the exact values, obviously 1/2 is 0.5, but √3/2 is 0.86. So I can see that this one here is √3/2, -√3/2, -√3/2, and +√3/2. And then the same for √2/2, that's the 0.7. So this one's √2/2, -√2/2, -√2/2, and just √2/2. So I put those into my calculator and I graph them, and I can see here the graph of a cosine curve. So this is just one full turn of the unit circle connecting the dots. The graph is going to look like that. So that's what a cosine graph would look like. Let's examine some of the parts. So a couple of things that we need to notice. First of all, the starting point. This is really important and it will come into play a little later. Cosine starts at a maximum. So since it's the highest point, obviously from that point it's going to go down. So you can see it starts at the maximum. So you can see this graph here. It looks very fluid from 0 to 2 pi or 0 to 360, but it's actually split into 4 sections. So if we look at those 4 sections right here. Now it's split into 4 sections because there are 4 quadrants. So that's why there's 4 sections to the graph, representing the 4 quadrants on a Cartesian plane. So in the first quadrant here, this would be quadrant number 1. You can see in quadrant number 1, it goes from a max to a midline. That's quadrant number 1. In quadrant number 2 over here, you can see it goes from the midline to the minimum. In quadrant number 3, it goes from the minimum to from the minimum back up to the midline. And in quadrant number 4, it goes from the midline up to a maximum. So it takes 2 pi radians or 360 degrees to complete one full cycle. The other thing I want to notice is that it has x-intercepts, and the x-intercepts are at pi/2 and 3 pi/2. Those are my quadrantal angles on the unit circle. And this is going to be the point here at pi/2 is going to be the point 0 and 1. So that's why it would be an x-intercept, because cosine has a value of 0. Okay, let's do the same thing for sine. So back to the unit circle. This time I'm going to do sine. So I'm going to put all of the x-coordinates, and we'll do this one in radians this time. We'll put all of the x-coordinates here, and these will be in radians. Little typo there you guys can correct in your notes. So this will be in radians. And then the y-coordinate will be in the sine value of those radians. So for example, I'm going to plot the point 0 and 0, pi/6 and 1/2, pi/4 and pi/2. √2/2. Same thing I did before, just in radians. So here I have all of my radians. Here I have my sine, the corresponding sine, again attached to those exact values. And this is what the sine graph looks like. So kind of connecting the dots, I have a hill and then I have a valley. So again, just like we did for cosine, let's look at the parts of that graph. Now again, the starting point, super important. Sine starts a midline right here on an upswing, just meaning it's increasing to a maximum. So just like for cosine, the graph of sine is split into quadrants. So we can look at the quadrants here, the 4 different sections of the graph, split into 4 sections again because I have 4 quadrants. So in quadrant number 1, I'm going from midline up to the maximum. In quadrant 2, I'm going from the maximum down to the midline. In quadrant 3, I'm going from the midline down to the min. And in quadrant 4, I go from the minimum back up to the midline, which is my starting point. So you can see it does take 2 pi radians to complete 1 full cycle of sine. So sine has x-intercepts at 0, pi, and 2 pi. So 0 where it starts, pi, and 2 pi. So those correspond to the quadrantal angles 0, pi, and 2 pi, or 0, 180, and 360. And that is when the sine value is 0. Okay, so putting it together here, cosine has intercepts at pi over 2, 3 pi over 2, 90, or 270. Sine has x-intercepts at 0, pi, and 2 pi, or 0, pi, and 360. So I don't know if you noticed this, but the sine and cosine graph are very similar. The only difference between them is actually the starting point. So if I were to take the sine graph, see the sine graph there in red, and I were to shift it pi over 2 units to the left, so if I were to take each one of these points pi over 2 to the left, I were to take this point pi over 2 to the left, I were to take this point here pi over 2 to the left, I get a cosine graph. So cosine is the graph of sine horizontally translated pi over 2 to the left. So let's look at how they're same and how they're different. So here's the graph side by side. They're both periodic functions, which just means they repeat over a regular interval, and we know that that regular interval is 2 pi or 360 degrees. They both have a max of 1, a min of -1, and that again corresponds to your quadrantal angles on the unit circle. They have an amplitude of 1. Amplitude again is the vertical distance between midline and max, or midline and min. Here's how they're different. Sine starts midline on an upswing. The start point is midline on an upswing. Cosine starts maximum, and obviously since it's the highest point, it would be a max and a downswing. So they have different starting points. Because they have different starting points, they also have different x-intercepts. So sine has its x-intercepts at 0, pi, and 2 pi. Cosine has its x-intercepts at pi over 2 and 3 pi over 2. So again, if you think in terms of the unit circle, every time I hit a quadrantal angle, one of the graphs is having an x-intercept. So at 0, that's a sine x-intercept. Pi over 2, that's a cosine x-intercept. Pi is a sine x-intercept. And 3 pi over 2 is a cosine x-intercept back up to 2 pi, which is a sine x-intercept. So on all the quadrantal angles, I'm having an x-intercept. Now, we only looked at the positive angles, but using coterminal angles, we can graph positive and negative sine curves. So you see here the sine curve like this. That's what we did one turn of the unit circle in a counterclockwise direction, but I can also go clockwise, and this clockwise direction would be on the other side like this, going around the unit circle. Same thing for cosine. We looked at a counterclockwise turn on the unit circle, but I can also look at a counterclockwise turn there. And again, because they are periodic, they do repeat on both sides. Okay, so back to chapter 1. Always comes back to transformations, doesn't it? Okay, we had that f of x in the transformed form can become this. Same thing we're going to look at with sine and cosine. So our function is now going to be sine and cosine. We just have a little bit of a difference here. So in this lesson, we're going to focus on a and b. Now, a in trigonometry has a special name. So normally we have a, vertical stretch and reflection, b, horizontal stretch, horizontal reflection, horizontal translation, vertical translation. In trigonometry, they all have different names. They all have special names. So in trigonometry, a is called the amplitude. So everything except for b has a special name. So a has a special name, h and k, which we'll learn in the next lesson, also have a special name. B stays the same. Okay, so what I want to look at is we're going to investigate what A does. What is the amplitude all about? So you can see here, it looks very pretty, doesn't it? I have 4 different graphs, and they're all color coordinated for you. So in the middle, the blue graph is your base cosine function. So let's look at when I graph 2 cos x, which is the red graph. So the very first difference that I see is that it's much taller. Okay, so it comes up here to a height of 2 and down here to a low point of -2. Looking at the green graph, a half, it's much smaller. So I can see that graph here has a height of a half and a low point of -1/2. And then the purple graph, negative cos x, we of course know that the negative a value is a vertical reflection, and I can see that it has been reflected. You can see the blue has a height of 1, reflected to have a low point of -1. So it looks like that A graph is affecting how tall the graph is. Let's look at a table of values here, or a table here comparing the different points. Now, the base graph, I really recommend memorizing this here. So first of all, cosine has a domain of all real numbers. There's no restriction on the domain. The range is in between low point and high point, which we saw was between -1 and 1. The amplitude, let's just go back to that. Amplitude is the distance between the midline and the max, and that has a distance of 1. So I know the amplitude is 1. The period is just 2 pi. It takes 2 pi to repeat the cycle. Now let's compare that to 2 cos x. 2 cos x, of course, was this red graph here. So I can see, looking at that table, the domain is not changed. The period is not changed. What is changed is the amplitude. So from the midline here, midline, to the maximum point, that is now a height of 2. So domain and period are staying the same, but the amplitude is 2. I had a low point of -2 and a high point of +2. Okay, let's look at the graph of a half. So back over here, I'm just going to erase, I have a lot going on here. So for the half, that's the green graph. You can see from the midline to the maximum, that's a half. It has a height of a half. So a high point of a half and a low point of -1/2. Again, the period and the domain are not changing. So domain and period are not changing for any of these graphs, in fact. So for the half, it had an amplitude of a half, had a low point of -1/2, a high point of +1/2. And then the last one for negative cos x, let's go to that. That is my purple graph. So that's just a reflection in the x-axis compared to the blue graph. So I can see it has a high point of 1, a low point of -1. So it looks like it has the same properties as the blue graph. It's just been reflected. So I would expect everything would be the same. So the range and the amplitude would be the same. So what I'm noticing here is that the domain and period are the same. It's the range and amplitude that are different. Now let's see if that's true for sine. So looking at sine here, I have 4 different equations. So I have sine x in the middle there, that blue graph is the base function. So when I have 2 sine x, the red graph, yes, just like the cosine, much higher. The green graph, a half, I can see, yes, it's much lower. And then, of course, I have my reflection in the x-axis. So it looks like the a value for sine is behaving the same as it was for cosine. So let's go and look at that table. So again, the domain for all of these is remaining unchanged, as is the period. So it doesn't look like that a value is affecting any of those. The range. So my base function for sine went from -1 to 1. So my amplitude, back over here, amplitude is the distance from the midline to the max. So that is also an amplitude of 1. My red graph, 2 sine x, went from -2 to +2, and the amplitude from midline to max was 2. So it looks like this is behaving exactly like a cosine graph. So the half went from -1/2 to +1/2, so the amplitude is a half. And negative sine x was the same as sine x, it was just reflected in the x-axis. So let's put this all together. The effects of a. So it looks like a, just like every other function, is the vertical stretch factor. So it's stretching it about the x-axis. If a is negative, there's also a vertical reflection. So xy becomes xay. So a affects all of the y values, such as max, min, range, y-intercept. The range becomes from negative a to positive a, and again we said we call that the amplitude. So to figure what the amplitude is, I look at the maximum point minus the minimum point divided by 2. Now I put those in absolute value just to remind you that a itself, amplitude, is the number. If it's a negative, it just means reflection. And remember from chapter 1, vertical is straight up. It's exactly as we would think it would appear. So let's try this. Describe the changes that have occurred compared to sine x or cos x. So if I have 3 sine x, this here is a vertical stretch, and it will be about the x-axis. Remember our RISA, we stretch about by a factor of 3. Okay, this one over here is a vertical stretch about the x-axis again by a factor of 3/4. Okay, so now let's look at our b factor. So b on the inside there. Let's see what's happening with that. We know from chapter 1, b is usually your horizontal stretch. So let's look if that stays true here. So purple graph in the middle is your base graph, cos of x. So cos of 2x, remember, because it's horizontal, I should expect it to be different. So let's see if it is in fact a horizontal stretch by a factor of 1/2. So the red graph, I can see, yes, it comes in half of what it was before. Okay, the green graph, the b value is 1/2, so that should be a horizontal stretch by a factor of 2. So compared to the original graph, I can see it's double the distance that it was. So distance of here becomes a distance twice as much. Distance here becomes a distance twice as much. So it does in fact look like it is behaving as we would expect it to in chapter 1. The negative x is a horizontal reflection. Now you can see that that graph is the exact same as the original. So I have 4 equations, but only 3 graphs. So when I take this and reflect it about the y-axis, it stays the same, which really tells me, since they are the same, that cosine is symmetrical about the y-axis. So let's go back to that table and see what affects b. Okay, so b, stretching it, does not affect the domain. Stretching it does not affect the height, so it doesn't affect the range. Horizontally stretching it, it doesn't affect the amplitude. Let's go back here and see it definitely affects the period, which is the time that it takes. So the purple graph is the base graph, and I can see from start point to end point, it goes from 0 to 2 pi. So my original graph has a period of 2 pi, as does my horizontal reflection. Okay, let's look at the period for 2x. So cos of 2x. So looking at that, that's the red graph. So start point to end point. So I start at a max and I come back up to a max, goes from 0 to pi. So that one has a period of pi. And let's look at the cos of 1/2 x. So looking at that one, that's the green graph. Let's look. It starts here. Well, I don't see another max, so I'm going to go from minimum, coming up, curving, going down to the next minimum. That goes from negative 2 pi to positive 2 pi. So that whole distance there, 2 pi to the left, 2 pi to the right, is 4 pi altogether. So the period would be 4 pi. So it looks like what's affected by the b value is the period. So the horizontal stretch factor affects the period. So 2 pi times the horizontal stretch factor is the new period. So let's look. This here, a factor of 2, has a horizontal stretch of 1/2. So if I take half of 2 pi, I do in fact get pi. Here, if I have half, my horizontal stretch factor is 2. So if I take 2 times the period of 2 pi, I do in fact get 4 pi. So it looks like that works. Now remember, horizontal lies, so everything should be opposite of what we think. Let's see if the same is true for sine graphs. So the base graph there in blue, sine of 2x. Knowing what I know about horizontal, it should be a horizontal stretch by a factor of a half, and I can see that it is. So this point here is half of the distance. Here, this should be a horizontal stretch by a factor of 2. So I can see that this distance here is twice the distance. So it looks like it works. And then a horizontal reflection. So having a horizontal reflection is just taking my base graph and reflecting it about the y-axis. So because I have 4 equations, 4 different graphs, I know that sine is not symmetrical about y. So it looks like that's only something that happens with cosine. Okay, so filling in the table. So again, we know in this table here that the domain is not affected. So the domain will be the same. Learning what we did from cosine, the range is also not affected because that's a vertical quantity. Neither is the amplitude. So it looks like it's going to be the period. So let's try that little trick with horizontal stretch factor. So if I have 2x, it's a horizontal stretch by a factor of a half. So if I take half of the period, I should have a period of pi. Looks like it worked. Horizontal stretch by a factor of 2, 2 times pi, I should have a period of 4 pi. Looks like it works. And then the period is the same. I've just been reflecting it, so it should have the same. So it looks like this is working. So period is going to be 2 pi times 1 over the absolute value of b. I put the absolute value there so that you remember that the only time we use the negative for a b value is when I have a reflection. So really, period is 2 pi divided by my b value. So putting it all together, effects of b. It's a horizontal stretch by a factor of 1 over absolute value of b. So again, don't include the sign. If b is negative, this is where the sign comes in, it just means there's a reflection in the y-axis. So b affects the period, but b is not the period. That's a really important distinction. Remember, horizontal lies like Pinocchio. So it's opposite of what we would think. So period is 2 pi divided by b. If we want to look what b really is, rearranging my formula for b, you can see that b is equal to 2 pi over b. Now, this one is on the formula sheet. This one is not on the formula sheet, but it's really not that hard to remember. Just remember that 2 pi is always on top. So whether I'm solving for period or b, it's always on top. So if b is not the period, you might be thinking, well, what is b? b is actually equal to the number of cycles in 2 pi radians. What I mean by that is b tells me how many times does this graph repeat itself in 2 pi radians. So let's do a question here. So I want to describe the changes that have occurred with this graph here. So when I have y equals cos 5x, this is going to be a horizontal stretch by a factor of horizontal lies 1/5, and that will be about the y-axis. For the next one, I have a b value of 1/4, so this also will be a horizontal stretch by a factor of horizontal lies. So instead of 1/4, it'll be 4, and that will be again about the y-axis. Okay, let's try a question with both an a and a b value. So I want to state the domain, the range, the amplitude, period, x-intercepts, y-intercepts of this graph here. So I have an a value of 4 and a b value of 1/3. Okay, so that's going to be my horizontal stretch and my vertical stretch. Okay, so when b is equal to 3, I'm going to say it's the horizontal stretch of 1/3. When a is 4, it's going to be a vertical stretch by a factor of 4. So Nothing affects the domain. So the domain is just going to be, you could say from negative infinity to positive infinity, or you could say the set of all x such that x is an element of the reals. Okay, my period is affected by my b value. So that's going to be 2 pi over my b value of 3. Or I can say 2 pi multiplied by my horizontal stretch factor of a third. Whichever way you want to do it, you're going to get period of 2 pi over 3. Okay, y-intercept, you need to know where sine starts. It starts at the midline, which has a y-intercept and an x-intercept of 0, 0. So if I stretch that vertically or horizontally, it doesn't change it. So that is my y-intercept. Now let's look at my x-intercepts. These are the ones that I wanted you to commit to memory. So sine has x-intercepts at 0, pi, and 2 pi. So what's going to change that is not the vertical stretch, but the horizontal stretch. So the horizontal stretch of a third, I'm going to, these are the old ones, these are the new ones, I'm going to stretch each of those x-intercepts by a factor of a third. So 0 times a third, 0. Pi times a third, pi over 3. 2 pi stretched by a third is 2 pi over 3. Those would be my new x-intercepts. Okay, so let's look now at a cosine graph. So we've done a sine graph with a and b. Let's look at a cosine graph. So I want to look at a full cycle, graph one full cycle of y equals to 2 cos of 2x. So first thing that I look at is, let's look at my vertical stretch factor. So my vertical stretch factor of 2. Now cosine starts at a maximum, normally at 1, but I'm going to vertically stretch that by a factor of 2. Okay, so I know that that's going to be my start point, and in fact that is going to be my new maximum. So I'll just draw like that so I know that that will be my maximum. Now normally my minimum is at -1, but I've vertically stretched it by a factor of 2, so that will be my new minimum. Okay, let's think about the x-intercepts. You have to commit these to memories. Normally, the x-intercepts of cosine are at pi over 2 and 3 pi over 2. But I have a b value of 2, which means I horizontally stretch those by a factor of a half. So instead of being at pi over 2, it's going to be half of that distance here, which is actually at pi over 4. Okay, same thing for the next one. I'm going to take that x-intercept at 3 pi over 2, and I'm going to stretch it to be half of the distance. So half of the distance, you can even count 1, 2, 3, 4, 5, 6. Half of the distance will be 1, 2, 3. So this will be my new x-intercept here. Okay, at 3 pi over 4. Okay, so that's really enough that we can now actually graph it. So I'm going to do maximum down to my midline, down to my minimum, come back up to my midline, and then I'm going to end at my maximum right there. Now, how did I know I'm going to end at pi? Well, normally the period of cosine is 2 pi, but I multiply it by my horizontal stretch factor, so I know my period is equal to pi. So that is one full cycle. What I could do if I wanted to finish off the graph is I could just copy that over like that. Oh, I'm missing a piece, it looks like. There we are. Let's put that together. And then I could actually also copy it the other way. I know we only asked to do one, but let's look at another one. So if I wanted to do it that way, I could also do it in the negative direction and then repeat it. So this is really nice here when I do the copy paste, because then you can see it's actually the same thing repeated over and over. So one full cycle is all I asked, but no extra charge for all those extra ones. So let's look at a summary here. So the graph of cosine and sine are obtained by using the unit circle. So I thought that was really important that you guys see, where do these graphs come from? So graphing the points theta sine theta and theta cos theta. A, we've learned, is the A value. It's the vertical stretch called amplitude in trigonometry. B, that's the only one that doesn't have a special name in trig. You could say it's left out, or maybe it's special because it's the only one that stays the same. The b value is the number of times the graph repeats itself within the period cycle, also the horizontal stretch factor, used to figure out period. So period is 2 pi divided by b, or 360 divided by b, but again, b itself is not the period. Okay, I know you guys already think I'm a little crazy with my math jokes, but did you know that math puns are actually the first sign of madness?